All right, this is the rest of section 10.3 handout, example 6 and example 7. So first, let's assume this is my velocity vector for the wind, and then I have some airplane. Let's say the airplane's going in this direction, u. So first, what's the speed of the wind? That's just going to be magnitude of the velocity vector. Oh, and as a side note, if you haven't already tried these, I'd say put these on pause first and try it, and then just use this as a check. Okay, and then the speed of the plane's tailwind. So notice I can only call it a tailwind because this is an acute angle. Otherwise it would be a headwind, but we're assuming it's an acute angle here. Theta and the speed of the plane's tailwind, what we're really looking for is, first let's sketch what the tailwind's going to look like. I'm going to take the velocity vector and I want to project it. So let's get a color I can do. I'm just going to make a little dotted line here that goes in the direction of the airplane. And then I'm going to project the velocity vector this way. And so this is going to be the tailwind component because it's the component of the wind that's going in the direction of the airplane. And so if I want that velocity, that's the same as asking for the projection onto the vector u of the vector v. And so we've done that before. Remember, that's defined as u dotted with v over the magnitude of u. And then it's in the direction of u, so that will be this. But notice this is going to simplify because we said u is a unit vector. And that means that both of these components are just going to be 1. So this whole thing is just going to simplify to be the dot product of u and the wind's velocity. And then that'll be the magnitude piece, and then this is going to be the direction. Okay, and then if we want the decomposition, that's the velocity of the plane's tailwind, so that's part C. So the speed of the plane's tailwind, that will be the magnitude of this projection, which in this case is just going to be u dotted with v. And I'm not putting absolute value bars around that because we're assuming it's a tailwind, and in that case I'm assuming this is an acute angle, so I'm assuming that the dot product is positive. Otherwise we would be calling it a headwind. Okay, find the decomposition of the wind vector. So now what I'd like to do is find this vector here, which is, when you notice if I take the red and the green and add them together, I'll get back to the blue vector. So the blue vector is equal to this projection vector, projection onto u of v, plus what we call the orthogonal projection of v onto u. And we can find that by just using vector subtraction. So that's just going to be equal to my original vector minus the projection vector, which in this case we have as this dot product and then times the vector u. All right, and then what if the plane's direction hadn't been a unit vector? Like if the plane's direction had been the direction A, we can just make it one, make it a unit vector. So let u be A divided by the magnitude of A, and then all of this works. And I like to point this out because when you're doing projections onto a unit vector, your projection is very simplified. It's just the dot product times that unit vector. And same thing, your component is very simplified. It's just the dot product. So this is a nice application of the dot product, and oftentimes when I have these problems, I'll just automatically make the vector I'm projecting onto a unit vector just to make my calculations simpler. Okay, and then the last application is work. And so for those of you that haven't seen work yet, work is a measure of the energy required to apply a force to an object through a displacement. And the definition, usually when I ask students that, the first thing they say is force times distance. That's going to be true if your force is applied in the same direction as your displacement of your object. But here you can see my force is applied at an angle. And so what we're actually going to do, here's the force vector, here's my displacement vector. So what I actually want is the component of the force that's in the direction of displacement. And we can see just from this picture, this is just going to be magnitude of F cosine theta. And then I'm going to multiply that by the distance, which in this case is going to be the magnitude of D, because that's my displacement vector. And notice this is actually just another way of writing the dot product, F dotted with your displacement vector. So this is a nice quick application of the dot product. And as an example, you can try the one below. I just give a basic force and a displacement vector, and we can see the total work is just going to be the dot product between the two. So I just multiply the I components, -2 times -4 is giving me 8. Adding the j components is 1 times 2, and the k components is going to be -2 times 0. So I end up with a total of 10. And I didn't have units on this, but if this was in newtons and if we were talking about things in meters, then this would be 10 Newton meters or 10 joules.